Download this code from codegive.com, link in the description below. Unicode normalization attacks, a deep dive and practical guide. Unicode, designed to represent all characters from all languages, is a cornerstone of modern software. However, its complexity opens the door to subtle vulnerabilities, specifically through Unicode normalization attacks. These attacks leverage the fact that some characters can be represented in multiple ways within Unicode, leading to inconsistencies in how strings are compared and interpreted. This can bypass security checks and filters, potentially leading to serious consequences. This tutorial will explore 1. What is Unicode and normalization, understanding the basics of character encoding and why normalization is crucial. 2. Types of Unicode normalization forms exploring NFC, NFD, nfkc, and nfkd with examples. 3. The problem, Unicode equivalence and security implications explaining how equivalent representations can bypass security measures. 4. Common attack scenarios detailed examples in different contexts, including file name validation, URL sanitization, and data filtering. 5. Code examples, Python practical demonstration of the attacks and mitigations using Python. 6. Mitigation techniques robust strategies for preventing Unicode normalization attacks. 7. Real-world examples and case studies illustrating real instances where these attacks have been exploited. 8. Best practices a summary of guidelines to ensure secure Unicode handling in your applications. 1. What is Unicode and normalization? Unicode a character encoding standard that aims to provide a unique code point for every character from every known written language. Unlike older standards like ASCII, which only supports a limited character set, Unicode allows for the representation of a vast array of characters, including emojis, mathematical symbols, and characters from languages like Chinese, Japanese, and Korean. Code point a unique numerical value assigned to a character in the Unicode standard. Code points are represented in hexadecimal notation, often with the prefix U+, example U plus 0041 for the uppercase letter A. Encoding the process of converting Unicode code points into a sequence of bytes that can be stored and transmitted. Common Unicode encodings include UTF-8, UTF-16, and UTF-32. UTF-8 is the most widely used encoding on the web due to its backward compatibility with ASCII and its efficiency in representing English characters. Normalization because some characters can be represented in multiple ways, composed versus decomposed forms. Normalization is the process of converting a string to a canonical or standard representation. This ensures that strings are compared consistently, regardless of their original representation. Without normalization, E could be encoded as a single code point, U plus 00E9, or as two code points, U plus 0065 for E followed by U plus 0301 for the combining acute accent. Without normalization, E and E \U0301 would be considered different strings, despite appearing visually identical. 2. Types of Unicode normalization forms ***. Unicode defines four main normalization forms, each with different properties. **NFC, normalization form canonical composition the most common form. It decomposes characters to their base forms and then recomposes them if possible. This means that E plus combining acute accent will be combined into E. NFC is often the recommended normalization form for general-purpose text processing. **NFD, normalization form canonical decomposition decomposes characters into their base forms and combining characters. Everything is broken down into its most basic components. E becomes E plus combining acute accent. nfkc, normalization form compatibility composition decomposes characters into their compatibility decompositions and then recomposes them if possible. Compatibility decompositions replace characters with visually similar characters but with different meanings. For example, the superscript 2, u plus 00b2, is decomposed to 2. It's important to note that nfkc may alter the meaning of the text, so it's generally not suitable for use cases where semantic accuracy is critical. *nfkd, normalization form compatibility decomposition decomposes characters into their compatibility decompositions. Similar to nfd, but it uses compatibility decompositions. The superscript 2, u plus 00b2, is decomposed to 2. Like nfkc, nfkd can change the meaning of the text. Example asterisk. Let's consider the character, u plus fb03, Latin small ligature ff. Asterisk original asterisk. Asterisk nfc asterisk, no change, as it's already in its composed form. Asterisk nfd asterisk, no change, it's considered a single code point. Asterisk nfkc asterisk ff, decomposed into 2 separate f characters. Asterisk nfkd asterisk ff, decomposed into 2 separate f characters. 3. The problem, Unicode equivalence and security implications asterisk asterisk. The core issue is that 2 strings that appear the same might have different Unicode representations. This means that standard string comparison operators, example == in Python, equals, in Java, will treat them as different. This can be exploited to bypass security checks that rely on direct string comparisons. Security implications asterisk. Asterisk file name validation bypass asterisk an attacker can upload a file with a carefully crafted file name that bypasses file name filters, potentially overwriting critical files or introducing malicious code. Asterisk URL sanitization bypass asterisk attackers can craft URLs that bypass sanitization routines, leading to cross-site scripting, XSS, or other vulnerabilities. Asterisk data filtering bypass asterisk attackers can inject malicious data into applications by using Unicode characters that are equivalent to blocked characters. This can lead to SQL injection or other code injection attacks. Asterisk authentication bypass asterisk in rare cases, if user accounts rely on string comparisons of usernames or passwords without proper normalization, an attacker could create a username that is visually identical to another user's username but has a different Unicode representation. This can potentially bypass authentication mechanisms. 4. Common attack scenarios asterisk asterisk. Let's explore specific attack scenarios in more detail. Asterisk scenario 1, file name validation bypass. Imagine an application that restricts uploaded file names to only contain alphanumeric characters and the period, dot. A naive implementation might use a regular expression like $AZAZ0-9 plus $ to validate file names. An attacker could exploit this by using a file name containing full-width characters, which are visually similar to ASCII characters but have different code points. For example, a.text, using full-width would bypass the filter because the regular expression only allows standard ASCII characters. After the file is uploaded, the application might process the file name, and if the underlying file system is not Unicode aware, or if the file name is later used in a context where normalization is not applied, it could lead to unexpected behavior. Asterisk scenario 2, URL sanitization bypass. A web application might have a URL sanitization routine to prevent XSS attacks. This routine might block URLs containing script tags or other potentially harmful code. An attacker could bypass this by using characters that are visually similar to and but have different Unicode representations. For example, the full width less than sign, U plus FF1C, and full width greater than sign, U plus FF1E, could be used in place of the standard AND. The sanitization routine might not recognize these characters, allowing the attacker to inject malicious code into the web page. Scenario 3, Data Filtering Bypass. An application might filter user input to prevent SQL injection attacks. This filter might block keywords like select, from, where, etc. An attacker could bypass this filter by using characters that are visually similar to the letters in these keywords but have different Unicode representations. For example, the Cyrillic letter, U plus 0410, is visually similar to the Latin letter A, U plus 0041. An attacker could use the Cyrillic A in place of the Latin A in a SQL injection attack, potentially bypassing the filter. 5. Code examples, Python. Let's demonstrate these attacks and mitigations using Python and the Unicode data library. Explanation asterisk. Asterisk demonstrate underscore normalization, text, asterisk this function prints the original string and its normalized forms, nfc, nfd, nfkc, nfkd, to illustrate how normalization changes the string's representation. Asterisk example 1 asterisk shows that E and E backslash U0301 are different, but NFC normalizes them to the same representation, allowing for proper comparison. Asterisk example 2 asterisk shows how full-width characters can bypass a naive file name validation check. nfkc normalization converts the full width to a standard A. Asterisk example 3 asterisk shows how ligatures can be handled. Asterisk example 4 asterisk demonstrates a vulnerable file name validation and shows how normalization, nfkc in this case, can fix it. This is the key to protecting against file name validation bypass attacks. Asterisk example 5 asterisk demonstrates how Cyrillic lookalikes can bypass a simple filter, and how to avoid it. Key takeaways from the code asterisk. Asterisk strings that appear the same can be different. Asterisk normalization can resolve these differences. Asterisk naive validation and filtering routines are easily bypassed. Asterisk always normalize strings before performing any security-sensitive operations. Asterisk choose the correct normalization form based on the context. 6. Mitigation techniques asterisk asterisk. The primary defense against Unicode normalization attacks is to normalize input strings before performing any security checks. Here's a breakdown of effective mitigation strategies. Asterisk normalize input early asterisk normalize all input strings as soon as they enter your application. This includes file names, URLs, user input, and any other data that is used in security-sensitive contexts. Asterisk choose the right normalization form asterisk. Asterisk NFC asterisk generally suitable for most use cases, especially when dealing with user-generated text or when you need to ensure consistent comparisons of strings. Asterisk nfkc/nfkd asterisk use with caution. They can change the meaning of the text. However, they are useful for cases where you want to remove compatibility characters or convert them to their closest ASCII equivalents. For example, nfkc can be useful in sanitizing file names or URLs when you want to restrict them to ASCII characters. Consider the implications carefully. Asterisk consistent normalization asterisk ensure that you use the same normalization form consistently throughout your application. Mixing different normalization forms can lead to unexpected behavior and vulnerabilities. Asterisk validate after normalization asterisk perform validation checks after normalizing the input. This ensures that the validation is performed on the canonical representation of the string, preventing bypasses. Use existing libraries. Leverage established libraries for Unicode handling and normalization. These libraries are typically well tested and provide robust implementations of the Unicode standard. Examples include Unicode data in Python, java.text.normalizer in Java, and the intl extension in PHP. Consider encoding. Be aware of the encoding you are using, UTF-8, UTF-16, etc. While normalization addresses equivalent representations within Unicode, incorrect encoding can lead to further issues. Ensure you are handling encoding correctly throughout your application. Principle of least privilege. Apply the principle of least privilege. Avoid granting excessive permissions to users or processes. This can limit the impact of a successful Unicode normalization attack. Regular security audits. Conduct regular security audits to identify and address potential Unicode normalization vulnerabilities in your application. Educate developers. Train developers about Unicode normalization attacks and the importance of secure Unicode handling. Consider regular expressions carefully. If using regular expressions, be mindful of character classes and Unicode properties. Use Unicode-aware regular expression engines and avoid relying solely on character ranges like AZAZ0-9 as these will not cover all possible characters. 7. Real-world examples and case studies. PHP null byte injection vulnerability. Although not directly related to Unicode normalization, this vulnerability demonstrates how unexpected character representations can be exploited. In older versions of PHP, a null byte, \0, in a file name could prematurely terminate the file name string, allowing attackers to bypass file name extensions restrictions. While Unicode normalization attacks use different techniques, the underlying principle is the same, exploiting subtle variations in character representations. File upload vulnerabilities. Many file upload vulnerabilities have been reported that exploit Unicode normalization. Attackers have used specially crafted file names to bypass file name filters and upload malicious files. This emphasizes the importance of normalizing file names before validation. SQL injection. Though less frequent, it's possible to construct SQL injection attacks using Unicode characters that bypass filters, as demonstrated in the code example. 8. Best practices. Always normalize user input. Treat user input as potentially malicious and normalize it before any processing. Choose the appropriate normalization form for your use case. NFC is generally recommended for most cases. Use well-vetted libraries for Unicode handling. Validate after normalization. Educate your development team about Unicode security issues. Perform regular security audits and penetration testing. By understanding the nuances of Unicode normalization and implementing robust mitigation techniques, you can significantly reduce the risk of these attacks and build more secure applications. Remember that secure Unicode handling is a crucial aspect of modern software development and should be treated as a critical security concern. Always stay updated with the latest research and best practices to protect your applications from evolving threats.